on the space of continuous function. Ah, nessuno mi ha corretto, on C00G, which is G invariant with respect to the left action. So first, what we can say about the existence, because we defined a measure, but we are not sure a priori that this measure exists. So maybe we are talking about angel sex or something like that. So a theorem of R is the following. So be precise. So let G be locally compact. Let's say also Hausdorff if we do not need it. Hausdorff group. Then there exists a unique left R measure on G. On G up to a positive scalar. We can dilate the measure using a positive real number, getting again a R measure. So somehow we take a locally compact Hausdorff group, we can talk about left R measure, and also we can talk about R Borel structure, because we can talk about R measurable set and blah. Okay? So proof? No. I'm not doing the proof because it's not so meaningful for the course. And so if you want to see a proof, maybe in the KNEP, so maybe, actually I do not know where to look specifically for a proof, a detailed proof for the R measure. Maybe KNEP or Elgerson, but I don't know. But so first let me give you some example regarding our measure. So first, not so astonishing. So the back measure for Rn is the translation. It's the unique measure up to scalar, which is translation invariant. So now maybe this example is more interesting, because I would like to spend you some time, in particular for those who want to solve the exercise, on this example, because you have to do we are going to show that for the positive real line and the plus, we are going to compute a linear function which realizes the R measure. And I'm saying that MF for any, let's say, for any F C00 Then we define mf, the integral from 0 to infinity, f x over x dx. Giusto?
Giusto.
And we claim that this linear functional is a left arm measure. Actually, I mean, left or right is equivalent because it's commutative, so it's not so important. And how can we do that? Say take A in here, so we have to apply L star A of M to F, which is what? F A times X over X dx. And now hopefully change of variable, Ax is equal to u. Vediamo un po'. No. Sì. Qualcosa non va. In casino. Allora. 1 su x. Copio, che faccio prima nella vita. A su Q. Oh, devo su A. Bene. Sono felice. So in particular, this is exactly n applied to f. Okay? So you see that somehow the idea is that you left translate the argument of your function and you somehow you need to pull it out without any effect on the integral. So for the exercise, I think the exercise 4.1 is use this example to compute the R measure on GLN R and see that this is inside GLN GL1 R, which is R star. So try to understand how to generalize this computation for GLN. Okay? Dove siamo? So in particular, one can ask, so far we have a statement about left R measure. Here it appears the word left. So one can ask, how can we define the notion of right R measure? So what we can do, let's check the top. So proposition the following. So numero 12. So let G be a locally compact locally compact Hausdorff group. And let M be the left R measure ho scritto on G. So we know that it exists by the theorem of R. So we can define M tilde of F. No, facciamo così. M check of F. M of F check where F check of X is defined by Fx minus 1. So we are on a group and we can define it. So the cool thing is that then M check is a right R measure. So somehow the inversion of the group can help you to build a new R measure, which this time is right invariant. So I mean that before we asked that the measure, the linear functional M, and hence the measure mu G is invariant by left translation. So if you use the same object but using this trick, then what you have automatically is that you obtain a right invariant measure, and hence in particular this theorem tells you that if there exists a left R measure, then you have also a right one and vice versa. But I'm not saying that they are equal. I'm saying that there is a way to pass from one to the other. So maybe the proof later, non adesso. Proof later, non adesso. Because right now I would really like to try to understand how far is a left invariant measure to be also right invariant. Clearly, if you have like an abelian group, then the product is commutative, so there is no such a big deal in order to get a measure which is both left and right invariant, but a priori is not clear why a left invariant measure should be also right invariant. And in order to measure, sorry for the word, in order to understand, let's say, how far is a left invariant measure also right invariant, we need to introduce the notion of modular function. So modular function. Questo me ne sbatto. Dove l'ho messo? Di qua. So let's ask again the question. The question is, let M be a left R measure on what? On a locally compact Hausdorff group how can we understand if M is also right invariant? So to answer to this question, we need to introduce these objects. So let's see. Let denote by how G, scusate, the set of the group of automorphism of G. What does it mean? So G is a topological group, so alpha is a homomorphism which is continuous, and admits an inverse which is continuous, so, and it's a morphism. And so take any alpha in Alp G right now. What we want to do, we want to define, so starting from M, we can define M alpha, which is a new linear function. I'll define as follows. M alpha of F, by definition, now, so here, suppose that G is the measure representing M. I need to write M alpha in terms of the measure mu G, and this is the integral of what? F alpha G voglio X. Tutte le volte mi sbaglio. This new object. So instead of looking at only X, we first apply alpha, then we evaluate the function here. So you can check. So you can check that M alpha is still left our measure. But this implies what? This implies that there exists a positive real number say lambda alpha, such that chiamiamolo proprio lambda alpha, such that M alpha can be written as lambda alpha times n. This is by uniqueness. Okay. So in particular, if we look at automorphism, we can modify somehow left arm measure and obtaining again a left arm measure, and the only thing that we are doing is to obtain a new multiplying with a real number which depends only on the automorphism alpha. So now the idea is what? Is the following. So, fermati. So, for any little g in G, we can consider the automorphism, the inner, facciamo che non esiste questa parola, the inner automorphism int G from G to itself in G of x G x G minus 1. So in particular we have a particular specific class of automorphism coming directly from G. So in particular, caspita cancello, di qua. In particular what we can say in this case, what we have is that we can restrict this particular case, this particular lambda, let's say, to the inner automorphism. That means, so if we apply to int G what we have said so far, we get a function, forse devo chiamarlo delta, vabbè, a function delta G from G to the positive real numbers given by what? Delta G is lambda in G, where lambda is the positive real number in the discussion above. In the previous discussion. Prima. Questo qua. Okay? So we are considering a particular class of automorphism, and we are considering this real number coming from the fact that if you perturb the left arm measure with by alpha, what you get is still a left arm measure. So the definition is, so this is, so lambda G is called modular function. And what? And a group G is unimodular if, by definition, our modular function is identically 1. So we are saying that a group is unimodular if the modular function is constant and each is equal to 1, for every element in the group G. So why the modular function is important and why unimodular groups are important. So first, somehow modular function measures how a left arm measure is far from being far from being right invariant. Indeed, if we write down, so we can write it down and we immediately see the point. Indeed, so c'ho questo, ma sì. So MF again is the integral over G by fx the G what? X. Okay? And now we need to take M alpha of f, where what? Where alpha is int G. So this is what? On one end we have, this is f alpha x demon G x. So we write down the definition of alpha, f g x g minus 1 demon gx. And now we can drop this g because mu g is left invariant. So this is my left invariance f x g minus 1 then mu g x. And here we can write m alpha of f is delta g of what? Of g, m of f, okay, and we can write delta g or little g integral f x demo g x. So here we have our right g to minus 1, which is exactly right translation by g minus 1, and here we have the modular function. So here somehow you can say, since they are equal, tutto uguale. They are equal, the modular function measure how the left arm measure mu g behaves with respect to the right translations. So in particular, we immediately see that if a modular function is identically 1, what we get that the integral of f x g minus 1 demo what? G x is equal to f x demo gx. Right? So in particular what we are saying that now our measure mu g is also right invariant. So unimodular groups are exactly those groups for which the arm measure, the left arm measure, is also right invariant. That's why that is the right definition to give. So we So we are going also to see so let me say this stuff is, even if it's maybe not the right time to speak about it. So modular function is crucially important for homogeneous spaces. So if you have a group acting transitively, we are going to say, well, what does it mean? Somewhere, so your space can be realized as suitably as a quotient of a group G by the stabilizer of a point. Here we are doing measure theory somehow, and you would like to do measure theory on quotients of your group G. And you can ask, well, here, let's say that, so let's say that we have, so please do not write this stuff because we are going to talk about later, but I want to give you a taste of what we are going to do. So if G is a locally compact group and you consider a closed subgroup there, you have a projection pi, and somehow you can ask, here we have a measure, I would like to induce a measure here, but in a coherent way, because here let's say that I have a left invariant measure and I would like to have a left invariant measure here. Is it possible? Is not possible? A natural question is which kind of condition I can have on both G and H in order to have an invariant measure on the quotient, and the crucial part, the crucial role in order to get an invariant measure on the quotient is played by the modular function of both G and H. I mean, I'm going to state a theorem from Paul, a theorem about the modular functions on both G and H in order to get an invariant measure on the quotient. And so we are going to see, for example, that for projective spaces or flat spaces, we do not have invariant measure, while, for instance, for, let's see, R2 minus the origin, we have invariant measure. Fico. So now, let me only state two things, and we are going to prove the other, I'm going to prove this maybe next time. So in order to conclude, let me state, so the exercise in the exercise sheet, so it should be exercise number 3, I think. And you need to check G locally compact. So point 1, I don't care, I don't remember. Point 2, show that this is a continuous morphism. So somehow the modular function is a continuous morphism into the positive real line. And to do this, you will need both the first point of the exercise, I don't remember, and the fact that in order to show the continuity of a morphism between topological group, the continuity, to prove continuity, it suffices to prove continuity at the neutral elements. And point 3 is somehow a way to understand. I mean, in here we have left translation, we have also right translation, but we have also inversion because we have a group. So we can ask how, if we use the inversion, how the integral behaves. And now this is the content of part 3 of the exercise. Fx dim gx is equal to what? dgx minus 1 fx minus 1 dim gx. So if we want to use the inverse to change the variable, let's say in our integral, we need to plug in also the modular function. So this is exercise 3. And let me conclude with some examples of unimodular group. Examples of unimodular group. So, as before we said that, for abelian group is not so astonishing that the right arm measure and the left one are exactly the same because of commutativity, so abelian groups are unimodular. And poi che ci mettiamo? 3 così, dal nulla. Compact group are unimodular. So if you take a compact group, what you can say is that it's unimodular, and essentially the trick is the fact that the function 1 is a continuous function with compact support. The group is compact, so not so. So in particular, what you get is that every compact group is unimodular, and one of the exercises, I think it's exercise 4, to show that GLNR is unimodular, actually GLN-F, where F is a suitable topological field of characteristic 0, or also QP, so GLN of QP is unimodular. So for 1 and 2, abelian and compact are can be seen somehow in a wider world of so-called amenable group. And amenable group are something like group which admits mean, where on L infinity. And they are quite useful in geometric structure in order to study specific quotients of Lie groups and blah blah blah. So they are quite important. Also compact groups are important. The fact that you have an R measure on a compact group also allows you also to study representation theory, because you have like Weil theorem, which tells you that representations are completely reducible because your group is compact and blah blah blah. And we will see that when we are going to study Lie groups, in order to build symmetric spaces, we will need every time a compact group inside our Lie groups. Our Lie group we are going to study. But one can ask if there is any other group which is not unimodular, because otherwise it's quite meaningless, the definition. The answer is yes, and this is exercise 4, last point. Show that the minimal parabolic subgroup of GLNR of order of GLL2 is not unimodular. So it's not true that closed subgroups of unimodular group are unimodular. It's not true a priori. You need to check it. Done. Ciao.